Hi everyone, today we're going to look at how to solve the heat equation for an infinite region, okay, where the initial condition is given as e negative exponent x, and you know that the solution here is bounded as x approach minus and positive infinity. Now for simplicity, I am going to consider my alpha equals to 1. Okay, so that my calculation will be easier. Okay, now if you look at that, for infinite region, the best way to solve this is using Fourier Transform. Okay, let's look at some of the definition of Fourier Transform that will be useful. So, if you are looking at the Fourier Transform of f(x), it is given as f omega f hat omega. These are the notation, and the definition for this is given as minus infinity to infinity fx e negative I omega x dx. Now similarly, if I'm looking at the inverse of f hat omega, this is given as fx, which is by definition is given by 1 over 2 pi minus infinity to infinity f hat omega e I omega x d omega. Okay, these are the few definitions that we need to use throughout solving this equation. Okay, now let's look at our equation here again. So we want to take the Fourier transform of ut equals to, now my alpha squared, alpha is only 1, so I have Fourier transform of uxx. Now one thing about the Fourier transform, the transform is applied to respect to x, not t. So in this case, all we have is the change from hat u with hat. So the Fourier transform of this will be u hat t omega t equals to, now the Fourier transform of this, okay, so let's recall the other definition given as, now the Fourier transform of the derivative given by I omega and f hat omega. Now this is a definition Fourier transform if you have n derivatives. So in this case here is uxx, which is second derivative. So by definition I have I omega because of the second derivative. And remember, f transform to f hat. Okay, f transform with f hat. So if I'm looking at u here, I will transform it with u hat omega t. Now simplifying this, I have ut hat omega t equals to negative omega squared u hat omega t. Okay, now to solve this equation, okay, to solve this, we can treat this as a first order equation. So this is first order homogeneous equation. So I can use either integrating factor or separable variable. For this simplicity, I'm going to just use separable variable. So separating the variable, okay, so in another word, this term here, they're not quite the same, but I can treat this as y prime over y equals to negative omega squared. Now integrating this will give me ln y equals to negative omega squared t. Okay, because respect to t here. Okay, so similar thing. So this one I have ln u hat omega t equals to negative omega squared t plus a constant a. Now taking the exponent, e negative omega squared t. Okay, so this is what we have obtained from the heat equation. Okay, so now we know that the initial condition is given as ux0 equals to exponent negative modulus x. So we cannot apply t to this equation yet. Let's call this equation 1. Because this is u hat. So what you need to do, you need to apply a Fourier transform to the initial condition. Fourier transform of e negative x. Now taking the Fourier transform of u will give me u hat, x will become omega 0. Now Fourier transform of this, you can use the Fourier transform table, or I can use the definition. What does the definition say? The Fourier transform of fx is given, integrate from minus infinity to infinity fx, this term. So this, I think I'm going to just use that. So this one will be integrating minus infinity to infinity e negative modulus x e negative I omega x dx. I need to solve this. Okay, so solving for this, I'm removing the modulus sign here. Removing the modulus sign, so I have from minus infinity to 0 e negative x, negative will give me positive, e negative I omega x dx plus from 0 to infinity, now the positive, which is negative x e negative I omega x dx. Okay, so because we know the definition, so let me just write it out. The definition of this one is negative x for x less than 0 and x for x greater than 0. So first, for the negative region, which is this one, you have negative. So negative will be positive, and now you take the positive region here, which is the negative. Okay, now what you got to do is integrate this, which is not that difficult. So what we can do is, before we do anything, let's simplify this. I'm factoring out the x. Factoring out x, negative x. 1 plus I omega. Okay, by integrating this, and don't forget we have a negative x here. Okay, this is from 0 to infinity. Okay, now putting up the boundary. So we have e when x is 0, e 0 over 1 minus I omega, minus when e is negative infinity. I'm just going to put it here like this so that you know what I'm talking about. Plus, now when this is infinity, minus e0 over negative 1 plus I omega. Okay, e to the power 0, 1. Now this one tends to 0, this one tends to 0. Negative will leave me positive. Okay, now what we do here, we simplify this, the denominator, where I have 1 minus I omega, 1 plus I omega. This one will multiply with 1 plus I omega plus 1 minus I omega. Cancels out, that will give me 2 over 1 minus I squared omega squared. Now I squared is negative 1. So I have 2 over 1 plus omega squared. There you go. The Fourier transform of E negative modulus x is given by this equation. Now we need to know that if you refer to the Fourier table, if you refer to the Fourier transform table, you can actually see that from the table is given by 2a over omega squared plus a squared. Now by comparison, my a is 1 by comparing this with this. So when a is 1, you should get the same answer. Okay, so if the Fourier transform table is not given, you use the definition, but if the table is given, you just use the table. Okay, so where are we now? So we have transformed the boundaries, this one. So u hat omega 0 from the boundaries is given as, so what is this? So we have u hat omega 0 is given by 2 over omega squared 1. Now what is equation 1? Because we want to find a omega actually. Okay, so equation 1, if you look at earlier on, is u hat omega t, a omega, e negative omega squared t. U hat omega t equals to a omega e negative omega squared t. Now when t approaches 0, we have u hat omega 0 equals to, when t approaches 0, I have a omega, which is equals to e to the power 0 is 1. This is 1, so I have therefore a omega equals to 2 over omega squared plus 1. Okay, therefore my Fourier transform of this is given by a omega, which is this one, e negative omega squared t. Now this is not the answer because the answer is uxt, so you need to take the inverse of u hat omega t, which is the inverse of 2 over omega squared plus 1 e negative omega squared t. Now the inverse of this is uxt. Okay, now this is a bit tricky because we need to use the definition for the inverse. I have wrote it down earlier on. Let's look at it. The definition of the inverse is this one. 1 over this whole thing. 1 over 2 pi, infinity, f at omega. Whatever inside the bracket here will be my f at e I omega x d omega. Therefore, the inverse of this thing will be given as 1 over 2 pi from infinity to infinity, this whole thing here, 2 over omega squared plus 1 e negative omega squared t, e I omega x d omega. Okay, this is the definition, inverse. So simplifying what I have, uxt is given by 2 and 2 cancels out, 1 over pi minus infinity to infinity e negative omega squared t e I omega x over omega squared plus 1. There you go, this is your solution. So this is how you do it. You don't have to solve this equation, you can just leave it in the form of the integral. Okay, because you look at, you need to use integration by part, or which will be chaos if you try to solve this. Okay, so that's all. In the next video, I'll show about how to solve in a semi-infinite region. Thank you.